Homework 2.7, Inverse Functions, Video 1. Homework due Friday, May 22nd, 2020 at 11:59 p.m. And I forgot to change this, so let's go ahead and change that now. Now, this first video won't really have any specific homework problems assigned to it because it's merely a definition. Actually, we're going to try to formulate a natural definition to what inverse functions are, if we can even wrap our mind around what do we even mean by inverse functions. One way to think about inverses is actions that undo each other. For example, this morning as I was getting dressed, part of getting dressed was putting on my sock on my foot, then putting on my shoe. So let's think of that as an action. I put on my sock, and then I put on my shoe. Tonight, I need to do the inverse of that action. So how would that go? How would I do the inverse of putting on my sock first and then putting on my shoe second? I would probably unput on my shoe or take off my shoe first, then unput on my sock or take off my sock second. So that's an example of inverse actions, if you will. Some inverse actions are pretty easy to wrap your mind around. If you walk 5 feet to the left, and then the inverse of that would be walking 5 feet to the right, because it would take you back where you started. Or if one action is driving from your house to your job, then the inverse action would be from driving from your job back to your house. So what we can see about these inverse actions is that whatever one thing does, the inverse undoes it, and at the end, you're back where you started. So the shoe and sock example, my foot started out bare, put on the sock and then shoe, and when I inverted that action, took off the shoe and then the sock, my foot was bare again. Or if I were to start at home, and one action is driving from home to work, then when I do the inverse of that action, from work to home, I'm back where I started. So how does this translate into the realm of functions? Because it's hard to write a function that says put on your shoe or drive to work. Well, a function in the mathematical sense, in a computer sense, is a totally different thing. Actually, that would be more of a procedure, but let's not nitpick. So let's think about a certain function. Let's take a real simple function. Let's say we have a function that says, give me a number and I will add 7 to it. So for example, and I've got a picture over here drawn. I haven't shown you this mapping picture for functions. But basically, each blob represents a domain or a range, and the arrow represents the direction the function goes. For example, this arrow on top says, give me a number over here, I'll send it through this function, and the output will come over here. So for example, let's say we take that function f of x equals x plus 7, and we give it a number at random, say 5. And then we put the 5 into the function, and what will it come out as? Well, the function adds 7 to it, so it'll give us 12. Let's try another number like negative 3. If I put negative 3 into the f function, it'll add 7 to it. Negative 3 plus 7 is 4. Or something even a little bit crazier like, because remember, we can put anything into a function. So let's say I put like a 5w. I know that's a weird thing to put into a function, but I can try to add 7 to it. And I would get 5w plus 7. So if we think of this function as an action that says give me a number and I will do an action to it and turn it into something else, then this is a visual of that function with some specific inputs. 5 turns into 12, negative 3 turns into 4, 5w turns into 5w plus 7. If we want a function that's its inverse, it needs to go in the opposite direction. In other words, it needs to take these values and turn them back into these. For now, let's call that function g of x. So I need a function that will take 12 and turn it into 5, 4 and turn it into 3, and 5w plus 7 and turn it into 5w. Well, what can I do to these 3 expressions to turn them into these 3 expressions? Hint, from left to right, I added 7. You're probably thinking subtract 7 and you would be correct. So a function g of x equals x minus 7 should be the inverse of f of x equals x plus 7. Because whatever the f does to something, the g will undo it. Now we can check it with any number we want. Let's put 20 here. 20 plus 7 is 27. Now let's put the 27 here. 27 minus 7 takes us back to the 20 that we started with. Okay, so in terms of functions, inverse functions, or inverses, have to do with one function turning an input into an output, but the other function taking that output and turning it back into the input. Let's see if we can write something that resembles a definition. Let's think about this in terms of function composition. If we were to take any generic number, we'll call it x, and put it into the f function, that's what we basically did. Oops, I don't need another parenthesis there. Give me 1 second. So let's see if we can capture what we're trying to show here. What we were showing over there, going from left to right, is that if we take any input, we'll call it x, and put it into the first function, f, it'll give us an answer, such as turning 5 into 12. But the other function needs to take this answer and turn it back into what we started with. So the other function needs to take this output and turn it back into what we started with. So the f does something to this, whatever comes out goes into the other function and gives us back what we started with. But wait a second, isn't this the very definition of function composition? So we could say g of f of x equals x. But it works both ways. For example, let's say we started over here with 12 and gave it to the g and turned it into the 5. Guess what the f turns the 5 back into the 12. So it actually has to work in both directions, meaning if we take some generic input, and I'm going to go ahead and set up the function composition notation, give it into the other function first, g, take that answer and give it into the first function, we should get back what we started with. So visually what this is saying is, whatever you give one of the functions, the other one will undo it. Whatever you give the f, the g will undo it and give you back what you started with. And the same thing if you give it to the g first. So that's the first two parts of the definition of inverse functions. And those are the most important parts. The other two parts are necessary, but we don't worry about them nearly as much. So what is that other part? Well, I'm just clearing off this picture. I'm redrawing it without all the numbers and everything. There's the f of x, and there's the g of x. If we were to think of these as domains and ranges, which one would be the domain of f? In other words, which one represents the numbers going into the function? That would be the numbers over here. So this blob, if you will, is the domain of f of x. And where's the range of f of x? Where's the set representing the possible outputs? That would be over here. Range of f of x. But what are these relative to the other function? For example, does this represent the domain of g? No, these aren't representing what goes into the g function, they're representing what comes out of the g function. So the elements over here would represent the range of g of x. But over here, the elements going into g would represent the domain of g of x. And so for reasons we'll see before this series is over, in order to be inverse functions, one function's domain must match the other function's range. So we could say the domain of f of x equals the range of g of x. And there's actually an important reason why that has to be. Let's suppose they don't match. For example, let's say there's an element that belongs to the domain of f but doesn't belong to the range of g. Well, if it belongs to the domain of f, then we can put it into this function. But we can't get it back out because it can't come out from the g if it's not in the range of g. So the main reason the domains of one has to match the range of the other is to guarantee that whatever we put into one function, we can get out of the other. And it works in both directions. The fourth one is the domain of g of x. equals the range of f of x. Again, all that's saying is whatever we put into one function, we must be able to get out of the other. So on line 2 here, whatever we put into the g function must be able to come out of the f function. So it's important for the domain of one to match the range of the other. And when they don't, then functions aren't invertible. Functions don't have an inverse, even when you think they do. You'll see an example of that in a moment.